Next, I would like to discuss about the displacement currents. In EMT, we have three types of current. The firstly is the convection current. Hopefully, you still remember what is a convection current. The convection current is a type of current that will not obey the Ohm's law. That means it can exist within a vacuum or free space. For example, we have the electron beam. The second type of current is a conduction current that is normally exists within a conductor. For example, we have a DC currents. And the third type of current is what we call as a displacement current. Okay, this is our third currents. Basically, the displacement current occur when we supply the time varying currents. Okay, time varying source. So it can provide the displacement current. But where is the displacement current? Alright, so let's say when you supply the DC current to the lump element circuit, for example, we have inductance and capacitor. What happened? Because the inductor is developed by using a multiple loop. So when we supply the DC current, what happened is just the current will pass through. So the inductor will be short circuit. When we supply the DC current to the capacitor, what happened? Because the capacitor is designed by using two parallel metal plate and separated by a dielectric material. Dielectric means it prevents the flow of charge. That means there will no current flow. So what happened when we supply the DC current to the capacitor seems to be open circuit. However, when we supply the lump element component with the time invariant source, what happens is the inductor will not short circuit. It can have a certain potential across the inductors. And also, for the capacitor, the current can flow through the capacitor. The current flowing inside the capacitor is what we call as a displacement current. And how to analyze the displacement current in EMTs? So what we are going to do is we have to start the derivation from the continuity current equations. Okay, we already see this equation in our previous chapters. We have the divergence of J equal to negative del rho V over del T. Okay, this is a continuity current equations. And we can expand that the J, the current density, is basically equal to the curl of H. Okay, and then we have the vector identity, which is the divergence of curl of any vectors must be equal to 0. Alright, so we must fulfill this characteristic. Therefore, the divergence of curl H should be equal to 0. So we have to alter this function to be negative del rho V over del T plus del rho V over del T. So this one will become 0. And then we have to change that the negative del rho V over del T is basically equal to the divergence of J, and then del rho V over del T is basically del the divergence of D. I hope you still remember that rho V is equal to divergence D. So we have two different functions here. So one function related to the current density, another function related to the field density. So when we move the divergence for both left hand right hand side, so our conclusion is our curl H is equal to the J plus del D over del T, or is equal to JC plus JD. JC equal to the uh, conduction current density, while JD is the displacement current density. From this equation also, you can see that we can relate the magnetic field with the electric field. Or here, as we know that the conduction current density JC is equal to sigma E, while the JD in this case is a del D over del T. Or this is a displacement current density and this part is a conduction current density. Let's say you are given two different circuits. First, we have a circuit consists only a resistor, and the second circuit consists only a capacitor. Okay, for the first circuit, let's say you are given the time varying current source, and so there is the conduction current flowing through the resistor. For the second circuit, when we have a time varying current source, so let's say there is no losses here, so we have a displacement current flowing through the capacitor. Okay, let's say for the first case we have the sigma, and the second case we have the dielectric here, epsilons, and this is a capacitor, and it has certain surface area. So we can determine the conduction current as well as the displacement current. How to determine it? So by using this formula, the conduction current equal to the integration of the conduction current density that pass through the cross-section area of the conductor. To determine the displacement current is equal to the integration of the displacement current density that pass through the surface area of the capacitor. Alright, so the displacement current, basically the time varying magnetic field produced time varying electric field and vice versa. So we can relate the magnetic field with the electric field for the time varying current. Both conduction and displacement current are produced in time varying. Both conduction and displacement current are produced in time varying. Okay, depend on the situations. So the application is let's say when we have a good dielectric material, so the dielectric material has no loss or leakage, so the sigma or the conductivity will equal to 0. That means there is no leakage current, there is no conduction current. But in practical, we normally deal with a lossy dielectric material where the sigma is not equal to 0. It has a certain value. Let's see the example 4. Two thin parallel plates separated with distance d equal to 3 mm is applied with time varying voltage V equal to 50 sine 10 power of 3 volt. If the surface area of the plate is 5 cm square and epsilon equal to 2 epsilon naught inside the capacitor, that means the displacement current flowing inside the capacitor. Okay, in this case we have a capacitor that's supplied with a time varying voltage, so there must be a displacement current, and you are given the dimension about the surface area of the plate and also the distance between two plates and also the dielectric material between the plate, which is epsilon equal to 2 epsilon naught. So for the solution, first we have to determine the displacement current density. The formula is equal to basically del D over del T, or equal to epsilon del E over del T. So the ID is equal to the integration of JD dot ds. And we know that the electrical potential V is equal to E dot dl. And the E also equal to negative gradient of V. This is what you have learned in the chapter 4. And here the gradient is only depend on the distance between two plates, or in the Cartesian coordinate is just maybe the dz in the direction of z. So it's only dv over dl, because the dimension is fixed, so we can just write as a v over d because everything is fixed. So we put here the jd equal to epsilon del E over del T equal to epsilon del over del T, and we have E equal to V over D. So we got epsilon D del over del T V, because this is a constant. Epsilon over D is a constant. So V here is a time varying voltage. So when you solve the differentiation, you got this value. I'm not solving first. And then for the ID is equal to the integration of the current density dot the ds. The ds, okay, in this case the s is a constant. It's just a constant area, so we put as a s, and the jd is a jd. So when we solve this, we got id equal to 147.5 cos 10 power of 3 t nano ampere. This is basically a time varying currents. Okay, this is the displacement current. So this is for the case of a capacitor, the fixed size. So it's quite easy. If we see the displacement current, basically this is the dot product of two vectors, and it become only a magnitude. Because what? Because these two vectors have the same directions. It has the same unit vector. Let's say if the ds, the surface area is facing to the y-axis, so the jd should be in the same directions. That's why the dot product will become only a magnitudes. Okay, so please remember this.